Okay, so we're going to solve this problem where we need to show that m to the 17 times n minus m times n to the 17 is always divisible by 10, whichever integer values of m and n we have. And we'll prove this by splitting up into two different steps. So first of all, we'll show that it's divisible by 2, that it's an even number, then secondly, we'll show that it's divisible by 5. So combining those two facts, this means that it must be divisible by 10. So if we start by showing that it's divisible by 2, we can actually notice that there's a simple factorisation we can apply here, where we can take out a common factor of m and n, so this just gives us mn times m to the 16 minus n to the 16. Then from this expression we can see that in most cases if m or n are both even, then we're going to get an even number. So let's just write these out. You can have m is either odd or even, and similarly n is either odd or even. And if we put these just into a little table like this, you can see that if either of m or n are even, then we've got an even number multiplied by some other integers, so we've definitely got an even number in this case. And the only interesting one to consider is what happens if both m and n are odd. But in this case, we've got m to the 16 minus n to the 16. So here, m to the 16 is just an odd number raised to a power, so this is lots of odd numbers multiplied together. And similarly, n to the 16 is a different odd number multiplied by itself over and over. So both of these, m to the 16 and n to the 16, are both odd numbers. We have an odd number minus an odd number. So in this case, where m and n are both odd, we actually have that m to the 16 minus n to the 16 is going to be even. So this tells us then in all four possible scenarios that this product, or the original expression we're interested in, is definitely going to be even. Now, before we get on to showing that this is divisible by 5, we can do a bit more factorisation, which is going to help make our calculations a bit easier later on. So you may have spotted now that we've got m to the 16 minus n to the 16, which is actually a difference of two squares expression. So I'll write this as m to the 8 minus n to the 8 times m to the 8 plus n to the 8. So it's a difference of two squares with m to the 8 and n to the 8. And then we can do the same thing with our m to the 8 minus n to the 8. This is another difference of two squares expression. We can write this as m to the 4 minus n to the 4 times m to the 4 plus n to the 4. And we still need to multiply all of this by m to the 8 plus n to the 8. And we can keep going like this with m to the 4 minus n to the 4, which factorises as m squared minus n squared times m squared plus n squared. Then we get these ascending powers of m and n at the end of our expression, and we can apply one final difference of two squares to m squared minus n squared to write this all then as m minus n times m plus n times m squared plus n squared times m to the 4 plus n to the 4, and finally multiplied by m to the 8 plus n to the 8. So we'll be able to use this factorisation now to help us show that our original expression is always going to be divisible by 5. And now to do this, our approach relies on considering m and n modulo 5, so we're thinking about their remainder when you divide them both by 5. So the possible remainders you can get are either 0, 1, 2, 3 or 4 when you divide a number by 5, and similarly for n. So we've got 25 possible cases to consider here. But if we look at our nice factorisation of our original expression, we can read off a lot of these cases. It's going to be really clear that this is going to be divisible by 5. So for example, if m itself is actually divisible by 5, so this is saying that m is equivalent to 0 modulo 5, it has no remainder when you divide it by 5, we can tick off all 5 of these boxes immediately because this whole expression is multiplied by a multiple of 5, so it's definitely going to be a multiple of 5. And similarly, whenever n is equivalent to 0, so when n is a multiple of 5, you can see that this whole expression is also going to be a multiple of 5. Then if we look at our next factor where we've got m minus n, you can see that this is going to be equivalent to 0 modulo 5 if m and n both have the same remainder. So for example, if we have 1 and 1, and we subtract these, we're going to get the difference, m minus n, will be a multiple of 5. And similarly for 2 and 2, 3 and 3, or if the remainders are both 4. So this gives us some more cases just by considering the factor m minus n. But then if we look at the factor m plus n, this is telling us again that if we actually have something like, for example, 1 and 4, you add these together, the remainder of 1 and the remainder of 4 give us a 5. So actually in this case, m plus n is going to be a multiple of 5. And similarly for 2 and 3, 3 and 2, or 4 and 1. So you can see we've almost finished now, actually. And we can just look to our next one, m squared plus n squared. This factor tells us even more about some of these cases. So for example, if we have 2 and 1, let's look at 2 squared plus 1 squared. This gives us 5, which is definitely a multiple of 5. And similarly, 1 squared plus 2 squared is also 5. Then we can look at 3 and 1, so 3 squared plus 1 squared is 10, which is a multiple of 5, so we can tick off 3 and 1, and by symmetry we can also tick off 1 and 3. The sum of squares there is still going to be a multiple of 5. So then we just need to consider 2 and 4, so 2 squared plus 4 squared, 4 plus 16, this is 20, which is a multiple of 5, so we can tick off 2 and 4, and similarly also 4 and 2. Then the final case to consider is where we've got 3 and 4, so 3 squared plus 4 squared gives us 25, which is again a multiple of 5, so we can tick off our 3 and 4 and similarly our 4 and 3 pairs. So you can see in each of these cases actually we don't even need to consider some of these other factors. We can always say that m, n, m minus n, or m plus n, one of these is going to be a multiple of 5, and hence our overall product, which is equivalent to our original expression, is also going to be a multiple of 5. So we've seen earlier that the whole expression is always a multiple of 2, and the fact that it's a multiple of 2 and a multiple of 5 means that it's hence divisible by 10. It has to be a multiple of 10, regardless of the values of m and n.